this lesson on logs, we're going to apply what we've learned from the log laws and exponent laws and relations of exponential functions and log functions to solve some problems. There's a variety of different problems that come up. Typically, what will happen is there'll be an unknown exponent, and you'll use the power law, possibly some other log laws, to isolate and solve for that unknown exponent. Now, I've got a summary table here that you could pause and look at, but generally speaking, growth or decay represents some amount based on some initial amount with some factor representing growth if this base is more than 1, or decay if it's less than 1, and some time interval compared to a half-life or some growth rate or something like that. Similarly, I can write this with a base of e, and you'll recall that e is a constant approximated by 2.718. It's kind of like pi, it's an irrational number, and it represents continuous growth. So we're going to solve several problems, and at various points you may want to pause because I'm going to move fairly quickly to cover all of this. Step 1, radioactivity. I'm going to solve 2 problems. I've got a radioactive material called flinconium. It has a half-life of 47 years. The question is, how long does it take for a sample to decay to 15% of the original? So I write A equals A naught, half-life, so base half, T over big T. Now, notice that they don't tell me the original amount. So the original amount, let's use 100%, then the future amount, 15%. Now, I could also call this 1, in which case I would call that decimal 1/5. If you're not told an original amount, work with percentages. So 1/2. Now, I have the half-life. That's the denominator. What I want to solve for is T. So I'm going to isolate the 100 to this side by division. It's going to simplify my analysis. And sure, let's call this a decimal as well, since we're working with decimals there. T over 47. Okay, I'm going to need to make a bit of space. Hang on a second. Okay, back with you. And what I want to do is take log of both sides now. As long as I'm doing something equivalent on each side at the same time, then I'm maintaining equality. Over on the right side, I'm going to use the power rule to bring the exponent out as a coefficient. I want to isolate t, so let's leave t on the left by bringing 47 to the right, and we'll divide by log decimal 5. So we're going to turn our calculator on, pardon me, and let's see what that answer gives us. We have, I'm going to move that up just a little bit, there we are. We have 47 log decimal 1/5, close the bracket, there we are, divide by log decimal 5, close the bracket, equals 128.6. Okay, so time equals 128.6, the units are years, 128 years. Okay, you might want to pause, think about the reasonableness of that answer. Remember, half-life means half the sample would be gone, so in 47 years I'd be down to 50%, in another 47 years, half of 50%, 25%, etc. Now, compare that to this one. This is another half-life problem. Now this time I have some mathite, and I have 35 grams, and it decays to 15 grams. Let's set up our formula. It's a half-life again. This time, I don't know the half-life, but I do know the amount of time taken. So I just have to rearrange what's known and what I'm solving for. What's known is 20 on the numerator. What's unknown is t, the denominator. I'm going to divide both sides by 35. That's 15 over 35. Makes life easier to bring that to one side. And again, my unknowns in the exponent, I'm going to do logs. Now, let's simplify that. That's 3 over 7. This is 20 over t log half. So I took the log of the right side and used the power law at the same time. Okay. My unknown's on the denominator on the right, so let's bring it to the numerator of the left. Leave the rest of it alone on the right side. And I want to bring this log term here to the right side. If I'm going too fast, pause and study my work. And I'm going to enter this in the calculator. And it was 20 log, let's check, 1/2, 20 log 0.5, bracket, divide, log 3/7, close bracket, enter. 16.4. So 16.4 minutes is the half-life. Okay. In the next couple, I'm going to set them up, or ask you to set them up, pause, try them, and then compare to mine. Let's move on to investments. All right. We have two people's investments, Albert and Beth, and we want to compare them. And what we find out is that Albert's got $2,000, 6% compounded monthly, and Beth's got $2,100 at 5 3/4%. Hers is compounded continuously. Compounded continuously means use base E. Now, how long does it take for his investment to equal? So we want to have Albert's equal to Beth's. All right, pause this and write down Albert's and then rejoin me. Okay, how's that look? Notice that I'm dividing by 12 because this is a per annum interest and it's broken in 12 parts. So my compounding is 12 times the number of years. Now, Beth's, I'm going to discuss and talk out because this might be something kind of new for you. The base is not 1 plus something when it's continuous. What I do is I just use E and I enter the percentage as a decimal in the exponent right there. That's how you deal with it. The quoted percentage as a decimal in the exponent base of E. All right, so at this point, pause and try to work out a couple of next lines of solution and see how you do. All right. When there's a coefficient in front of each side, it's good to divide by one side or the other to remove it from one side. It simplifies the analysis. I also simplified the inside of this exponent to get the decimal 1.005, and the 2100 divide 2000 makes this decimal. Now at this point, we need to use logs, and I can use log base 10, or I could use log base 1.005, which is a little awkward, or I could use log base E, or ln, and that's what I'm going to do. So I'm going to write ln of 1.005 exponent 12t equals ln 1.05 e exponent 0575t. Okay, notice that it's the ln of the entire right side. Now think about what property I need to use on the right side, and I'd like you to simplify the right side a little bit using a log law and then rejoin me. All right. A common mistake people make is to use the power rule first. This exponent applies to this base, but not 1.05. Sometimes people write that exponent out front as a coefficient and then leave the remainder 1.05 in E, which is wrong. What you need to do is you need to use the product rule first. This is a product of things. The exponent is only on the second part of the product. So you need to first write as ln of the first factor plus ln of the second factor. Okay, now I'm going to carry this on the left side, and I'm going to write 12t ln 1.005 by using the power rule. Ln of E with this exponent is just 0.0575 t because the log base is the same as the base of the exponential. So I can simplify that a bit. All right. Now, I want to solve for time, and time is on the right and on the left. So I'm going to bring it all on the left side and factor it. 12 ln 1.005, subtract 0.0575, and the term without t stays on the right side. Lastly, t equals the right side divided by that bracket on the left side. I know it's a bit ugly, but we'll use our calculator in a moment. And let's see what that equals. Okay, I'm going to grab my calculator and move it over here so I don't block the view too badly. And let's see, we've got ln 1.05, close bracket, divide, open a bracket for the entire denominator. Make sure you're doing proper order of operations. And close that bracket, push enter, 20.76. Now let's just look at the context of the problem. This was how long it takes, and that's going to be years, so quite a while to get caught up. All right, a couple more problems here. Let's move on to cooling. So in this case, I have an oven that's originally hot, then turned off, and it's starting to cool off. I tell you that temperature depends on time, according to this relationship, and you're given some information about a later time and a later temperature. What I'd like you to try to do is pause the video, see if you can figure out what A is and what B is, at least, and then rejoin me. Alright, there's A done. I'm told at the start the temperature is 170, so substitute 170 for output or range, and a 0 exponent for the input. That leads to A is 170. Try B. Alright, in this case now I'm able to say 170 base B exponent T. I know temperature at 18 time is 42. Substitute these. 42, there's my 170 I knew, my 18. Isolate for B. Take the 18th root. Now we can do this on our calculator this way. I would write 42, or I would type 42 divided by 170 exponent 1/18th. That's the 18th root. And I would get decimal 9253. 9253. 9253. So I'm now able to say the temperature at any time is 170 decimal 9253 exponent time. That's describing how this oven cools. So part C says, how long does it take for the oven to reach 25 Celsius? Well, that's just a substitution into the equation that we've just created of 25 for the exponent. And we'll use our calculator and figure that out. So 170 bracket. Now, the base is right there, so I'm going to just go answer and reference what's already in my calculator. Then it's not rounded. And I get 24.4. 24.4 minutes. Alright, that's a cooling problem. Let's see here. We have, you know what, I'm going to do this question on another video, so I'm going to wrap this one up here so we're not too long.